Then write 13 in front of that 13 practical. Write down. We can quickly do this, right? Write down verification of combination between frequency and length of taut wire. Taut means it is under tension, right? Taut wire. Okay, so this is a verification. So if it is a verification, obviously we have to go for a graphical method, right? Right. So what is the verification? What do we have to verify? So V is tension divided by simple M, right? This is F times 2L. For this one also, we are using the same principle. We are going to have the fundamental frequency. So lambda is equal to 2L. Then this is frequency, right? So between frequency and L, we are going to verify the combination between frequency and the length. So here we are keeping this to be constant, velocity to be constant. So when you put F to this side, what do you get? What's the verification? I mean combination. Length is inversely proportional to F. You can say that, right? Because these two have a inversely proportional. You can subject L and F is below at the denominator. So you can say L is inversely proportional to L. So this is what you have to prove here. Length is resonance length. This is called resonance length, right? Not just length, resonance length. Length when they are resonating is proportional to 1 over the frequency. So that is what we are going to derive here. So the same stuff, sonometer, the pegs, you can draw this. With me, draw this. You have the pulley and you have the mg, then there's tension. Write down for sonometer wire between pegs when it makes a standing transverse wave at fundamental resonance frequency, comma, meaning that you are going to apply that V equals F lambda to this part, right? When it oscillates at the fundamental. So V equals F lambda. Lambda divided by 2 is the length of the wire, this part. Not the whole wire, right? Only this resonating part. So lambda is 2L. Just substitute. Mg of M is the velocity. Frequency. Lambda is 2L. Just hold on, right? 2L. But since we are in this practical, we are not going to change. We are not going to change any of these. We are not going to change the velocity, the load, any of them. we are going to change simple F and L, frequency and length. So in order to change the frequency, we are going to need a set of tuning forks, not just a one fork, right? Right. Since we are not going to change this, I am just keeping this to be V in this experiment, right? We are not changing any of this. This is a dead weight here. We are not changing this. So if you keep it constant, you can say V equals F times 2L. Okay. So what we are going to do here is, in the experiment, you have a set of tuning forks. You have a set of tuning forks, right? From smallest to largest. So you know, smallest one has the highest frequency, right? So you can gradually increase or decrease frequency. So depending on that, you get different resonating lengths here. So in order to resonate that, you still have a paper rider here, right? Identify the resonation. You are going to have different lengths here. For different forks, you place a fork, let's say 100 hertz. You need to adjust this length to be 100 hertz. Then there's resonation. Likewise, you have about, you need to take about 6 tuning forks, about 6 tuning forks in order to have different frequencies, right? So here you have to identify dependent and independent variable. So what is the variable we are changing? Easily we can choose a fork, right? You have a set of forks, you can choose a fork. You get the fork and you place it. So we are doing that, right? So F should be related to X. X means independent variable. Independent. This is stuff you can take if you want. I mean, as I'm explaining, L is dependent. L is dependent. So depending on the fork, resonating length changes, right? That's why we put this as Y. I mean related to Y, right? Then we can arrange this to have the exact thing there. Okay, just take it down and thumbs up once you're done. Just get this done now, right? You don't have again, you don't have a time to do this later. So under full focus, you have to understand these and listen, right? You have to have that. Right. Below this, right? Here, simple F is the independent variable. Independent variable. Within brackets, simple X. Within brackets, right? We change it. Close brackets. Then simple L should be the dependent variable. Within brackets, because it changes according to simple F. It changes according to simple F. Okay. So the graphical method, now we identified dependent and independent variables. Now we can build the theory. So we are keeping this. So usually this V, I'm going to subject that L. So F times 2 goes to the other side, right? So it becomes V over 2. You can write it as V over 2. Let's say like, otherwise you will. V over 2, just cross multiply, right? You had a subject L. V over 2F equals L by cross multiplying that. Then you can change sides. L is equal to what? V over 2. Instead of 1 over F, you can separately write it like this. Then frequency is related to the X, right? So you can say that this term is X. This term is Y. And the gradient becomes this. Purpose of this experiment is not to find the velocity, right? Purpose of this is to verify this, okay? But as an extra advantage, you will find the velocity of that as well. But it is not the purpose, right? Okay, so you draw, you just take it down and thumbs up. So it doesn't matter, it is the night time, right? Like you have to have the full focus, don't stay like drowsy, right? You need to have the full focus here, right? Then it is done. Once you have the full focus, it is done here, right? At the class itself. Right. Okay. So y equals mx. So we are going to draw a graph. Before drawing the graph, you need coordinates, meaning x and y coordinates. So how do you find that? That's why you need to do the experiment, right? So you get a one fork, and for that fork, you will find a resonating length. You mark it here. Then get the another fork, place it following the same procedure I explained earlier, right? Place the sonometer using resonance, mark the F value, frequency of the fork, L. Then like that, you need to get about six readings for F and L. But here it is L and 1 over F, right? But if you know F, you can easily calculate 1 over F values. Now you have y coordinates and x coordinates, 6 x and y coordinates. Then what do? Using those 6 coordinates, you can draw a graph. So this is L, this is 1 over F. So let's say you mark these coordinates like this. So at the first time, luckily, if you get something like this, draw the best fitted line. Then luckily, if it is go through 0, then you successfully verify if this is y equals mx. Once you verify this, you verify this. You can go backwards. You verify this one. You verified f proportional 1 over L. So that is how you do the verification. Take it down. First the table, then the graph, right? Below this, right? Below everything, right? Unlike in 12th means previous fraction. Unlike in 12th, graphical method is used here to verify combination between simple F and simple L. Right? So that is how you build up the theory in this experiment. So I told you that there is a set of tuning forks. Then we need to clarify some things about that set of tuning forks. Write down subtopic using set of tuning forks. Using set of tuning forks. Right. So in the lab, there's a small tuning fork, right? Small one. Smaller the fork, higher the frequency. Then slightly bigger, slightly bigger, slightly bigger, like that. You can draw this as I'm doing that. Sorry, not the stem, right? Sorry, wait. Stem does not matter, but these prongs, length of these prongs increases. Right? So to this side, frequency decreases. Okay? Time period increases. When it vibrates, time period increases. So this smallest one has highest frequency. Highest frequency. This has lowest frequency. Take it down. So this has the lengthiest one, right? Prongs. So if they are lengthier, what happens? When they vibrate, it is difficult to vibrate, right? So what happens? Time period is larger. It takes a long time to complete, not a long time compared to this. It takes a long time to complete one oscillation of the prong. So if the time period is larger for this one, what does it mean about frequency? Frequency is smallest here. If time period is largest, because you know this, right? F equals 1 over t. If time period is largest, frequency smallest, right? Now you have to understand that. Just remember, smallest one have the highest frequency. Okay, taking it down, right? Below that, right? When the length of prongs increases, their periodic time also increases. Their periodic time also increases. Likewise, frequency decreases. Right? First you have to understand that. Next point, right? Below that, right? Practical starts from the lowest frequency fork. Starts from the lowest frequency fork to make sure that the length of sonometer wire is enough when using all the forks. Another point, if the length is not enough, decrease capital M at the start of experiment. So the length of wire will be enough for all the forks. Right? So this is very important, right? You might not. Right. So you have this length, right? Sonometer wire length, right? Sonometer wire. So in this experiment, you have the set of forks. You know this combination? L is proportional to 1 over F. Inversely proportional. So they say, so you have a set of sonometers, right? Sorry, set of tuning forks. So for different tuning forks, you are going to need different lengths. So when the frequency decreases, length required increases, right? So what do? We get the smallest frequency. What does it mean? We get the smallest frequency. For the smallest frequency, we have the highest length, right? Let's say that is 50 centimeter. So for the smallest frequency, we have this highest length. So smallest frequency is this one, right? This one. So all the other ones, the frequency is higher. So for higher frequencies, we'll have the less lengths. So in the experiment, you have to first make sure that we can use all the tuning forks when you are doing the experiment. So what do? We get the largest, meaning lowest frequency tuning fork, and place it. So for that tuning fork, we will have the largest length. So for other tuning forks, length will be sufficient, right? Because for those, it is less length, right? So we start the practical. You have to first make sure that it is enough. So let's say it is not enough. You just keep increasing the length, still the paper rider does not fly away. There's no resonance still. Then what do? For the lowest frequency, you have the largest simple L. To get the largest one, you don't have enough length. Then again think about the equation. mg over m f times 2L. So what's the problem? In order to gain this lowest frequency, you don't have enough L. You can do this, right? You can decrease the load, right? So if you decrease the load with L, required length decreases. Okay? Required length decreases. So you have to decrease the capital M. So the required length decreases. You cannot change a simple F, right? Simple F for the fork. So at the start of experiment, you have to do this adjustment. If it is not enough, right? If the length is not enough, you have to you have to remove weights from the pan and make sure this length value will be sufficient, right? So if this is like 1 meter, you have to make sure by decreasing this, you get a 1 meter for this resonating length, right? It should be actually less than 1 meter, right? Because at the edges, we are not doing that. So like that. Write this equation down with the arrows under that point. Done. This equation only, right? With the arrows. So I can decrease the length. I explained that in the sentence. These are extremely important, right? They often ask these questions in the exam, okay? You can answer them only if you clearly understand these. So pay full attention. Right. So what did we do? We got the lowest frequency and make sure that the length is going to be enough for all the tuning fork. We still didn't start the experiment, right? We just make sure that the length is enough of the sonometer length is enough, right? But when you are doing the experiment, you have to start from the highest frequency. You are starting that from the highest frequency. Okay. Starting the experiment means you are starting to take measurements, right? In order to draw the graph. So you start with the highest frequency. Okay, write down. Take in measurements. Another point. Take in measurements. It starts from highest frequency fork. Highest frequency fork within brackets smallest one. Highest frequency fork within brackets is smallest one. In descending order of frequency. In descending order of frequency. So we make sure length is enough using this largest one. Then taking measurement is done starting from the largest frequency, smallest tuning fork. Right. Then draw a line to separate that. In the experiment, you need to make sure that all the resonating lengths are for the fundamental. Resonating lengths are for the fundamental. Right? So how do you make sure that? Now we are thinking about resonating, right? So for each, we start from the smallest value. Same as before, right? We start from the smallest value. Listen carefully. You have to get the bridges to the closest, right? Very close. Like this. You can draw this with me. Like this. It is a similar graph, similar diagram as earlier. You bring it to the closest, right? The pegs. Then let's say for this, you get 2000, 2F0, 3F0. So it is 4000, 6000. So the fork given is, for an example, this example, fork given is, it has 1000 hertz. Fork has 1000 hertz, right? We need to match this with these are frequencies of wire. So it is not enough. Then what do we do? We need to decrease the frequency of wire. How do we decrease that? By increasing the length. If we increase the length, frequency decreases. Because we need to get this frequency to 1000 hertz. Let's say we slightly increase the length by moving the peg. Then let's say it comes to 1500. Then 2F should be 3000. Then this should be 4500. Still we didn't get, right? Still we didn't get the resonance. Then we further increase that. Let's say now you got 1000, 2000, 3000. Now it matches with this 1000. Then resonate. Then you mark this length, right? This is the resonating length. Earlier ones are not resonating lengths, right? Those are just lengths. This is the resonating length. Then the frequency and the length. Now we have one value there. To fill the table, this is the value. 1000 and L, right? 1000 and L. So remember, we started from the largest frequency, right? Then to get the another fundamental, we have to get the in the descending order. We are taking forks at the descending order. Let's say you get a fork like 800 hertz. I'm using these numbers for the simplicity, right? Actually, there's no forks like 800, right? The forks are like 256, like that. Okay, so 800, I take a 800 hertz. Now I'm not changing this length, keeping the same distance. Now, we know F is 1 over L, right? Now the frequency has decreased. Frequency has decreased. So what should be if the frequency has decreased, what should be the frequency here remains at 1000, right? Frequency of the fork is decreased, but if you are keeping the same length, it is still 1000, right? And overtone becomes 2000. Another one 3000. But here it is not a resonating. Now it is not resonating, right? Because now it is 800. Fork is 800. This has these frequencies. So they don't match, so there's no resonation. So for resonation to happen, what you have to lower this value to 800 hertz. You can do that by increasing the length. Then the resonation, let's say, occurs now 800, 1600, 2400. Now the resonation occurs. So this is the second resonating length, L2. Then you mark that and the 800, right? Likewise, you need to get 6 cases, right? So you can understand that doing the experiment is not that easy, right? Right. Take this down and thumbs up if you have taken it down. These are not actual values, right? These are just to explain what you actually have to do in the experiment. So, Yehan sir, still taking notes? Chanuka, sorry. Right. You have to again revise this, right? And study what I just said, right? Okay. Then the last point of this experiment. So from the experiment, we saw that m dash is equal to v over 2, right? Remember? Gradient is equal to, m dash means gradient, v over 2. And we drew the graph. So from this, actually you can find velocity of the wave. So it is 2 m dash. M dash value is known, right? Write this down. So write down as an extra step, speed of transverse wave also can be found. Speed of transverse wave also can be found.